In this video, we will learn about modular multiplicative inverse and we will go through the concept and code. See, the reason we are not solving problem for this is that this is heavily used algorithm, and as we move forward, we will encounter so many applications of this and we will go through so many problems of this. Also, we will make separate videos on various important problem on modular multiplicative inverse. But in this particular video, we will completely focus on the concept and we will try to code it. We will look at two different approaches to solve this problem, and this is going to be the video that you need to completely understand the modular multiplicative inverse. So let's get started. So what is modular multiplicative inverse? So modular multiplicative inverse of an integer a is an integer x such that if you multiply a and x and take mod with m, you will get the value 1. So that's what modular multiplicative inverse is. X is going to be the modular multiplicative inverse of a. Simple as that, right? You multiply a into x and you take mod with m, and the remainder you will get it as 1. So there is a key observation. Modular multiplicative inverse doesn't always exist. So let's say you have m as 6 and a as 4. You cannot find x such that you multiply it with 4 and then you take mod with 6 and you will get remainder as 1. Try to find it. Also, pause this video here and try to prove this. See, we have already gone through linear Diophantine equation. I will put that into the card if you haven't gone through it. We have gone through Euclidean algorithm. Also, we have gone through the extended Euclidean algorithm. If you have understood those concepts, then you should be able to prove this particular observation. If you are unable to prove this particular observation, go ahead and watch those 3 videos and then come back here. I will teach you the proof. Okay. Hopefully, you have gone through the linear Diophantine equation, extended Euclidean algorithm, also Euclidean algorithm for GCD computation. So, okay, let's get started. So, modular inverse exists if and only if a and m are relatively prime. Okay, relatively prime. That means GCD of a and m is 1. Then only modular multiplicative inverse will exist. We will discuss why, but let's try to prove it first. Modular multiplicative inverse exists if and only if a and m are relatively prime. Right? That means GCD of a and m is 1. See, this is the equation that we have, right? And we need to find x. I can write it something like this. We have a into x. Then I am subtracting k into m from it and we will get 1 as the remainder. That's what the definition of modular multiplicative inverse is, right? This is something like this. A into x is going to be k into m plus 1. So I am just moving k into m here. So that's what I get. Now I can write it something like this. See, I have written it in this format purposefully because this perfectly matches with our linear Diophantine equation. So that's why I told you to go through the linear Diophantine equation first. So, for a solution to exist for this, GCD of a and b should divide c. Now c here is 1, b here is m, a is a. So GCD of a and m should be equal to 1. Why? Because c is 1 here. And to have a solution for this linear Diophantine equation, GCD of a comma b must divide the value of c. C is 1. So what divides 1? 1 only. That's why GCD of a comma m needs to be 1. And we have proved that. See, this is what we wanted to prove. Modular inverse exists if and only if a and m are relatively prime. So by using linear Diophantine equation and observation of a linear Diophantine equation, we managed to prove the solution exists. The inverse exists if and only if GCD of a and m is equal to 1. Okay, so the very first approach that we are going to follow is extended Euclidean algorithm so that we can compute the value of x. So we have this type of equation, right, in extended Euclidean algorithm, and we know how to solve it. Remember, GCD of a and m is 1, then only the solution is going to exist. By using extended Euclidean algorithm, you can directly find x and y that satisfies this particular equation. Remember, we use extended Euclidean algorithm to find GCD, to find x and to find y, so that a into x plus b into y is equal to g holds true. And we need to find x here. We have already managed to write this particular equation in this format while we are proving this particular observation. See, we managed to convert this particular expression into this expression. I'm just writing here a as a, for b as m, right, and g is going to be 1. For the solutions to exist, GCD of a and m needs to be 1. That means this particular equation that we have here exactly matches with this extended Euclidean algorithm equation, right? And we can get the solution by using extended Euclidean algorithm. See, g here is 1 only, right? Because GCD of a and m is going to be 1. Then only the solution exists. And you can compute GCD of a and m and check whether it's 1 or not. If it's not equal to 1, then solution doesn't exist. That means inverse doesn't exist. If it is 1, then you can simply compute the value of x by using extended Euclidean algorithm. Please watch extended Euclidean algorithm if you haven't gone through that particular topic, or if you are unable to understand it. First go through that video, come back here, watch this again, and if you are still unable to understand, please do comment. I will make a separate video explaining on every single thing here, right? Let's look at the code. You have a, you have m. Extended Euclidean algorithm will provide you the g, that is GCD, also provide you the x and y value. So it will give you g, y and x values, right? So let's check g is 1 or not. Remember, g needs to be 1 to have the solution. If not, then we are just going to return the -1. That means solution doesn't exist. Else, we are going to return x. But before we return x, we are doing something, right? We are converting negative x to positive ones by taking the mod. See, extended Euclidean algorithm determines the sign of x and y based on the sign of a and m. So x can be negative. So we are just converting it to the positive value and then we are returning it. The second approach that we have is using binary exponentiation. See, this is the problem that we need to solve. When GCD of a and m is 1, you can write this particular equation. This phi of m is called as Euler-Stoughton function, which tells you the count of numbers who are co-prime or relatively prime with m. I hope this makes sense. So, phi of m is m minus 1 when m is a prime number. This is a very important observation that we have here. See, for number 5, right? There are exactly 1, 2, 3 and 4 numbers, and all these numbers are relatively prime to 5. Why? Because 5 itself is a prime number. So, if m is prime, then phi of m is going to be m minus 1. So, this is the property that we get from Euler-Stoughton function. If GCD of a and m is 1, you can write something like this. Now, we can divide on both sides by a and you get something like this. We can write it something like this: a into a power phi minus 1, and here you will have 1 mod m. So this and this exactly matches. So this a matches with this a, and your value of x is going to be a power phi minus 1. 1 matches with 1 mod m, right? So the value of x is going to be phi a power phi minus 1. So phi of m is going to be m minus 1 when m is prime number. Otherwise, there exists different algorithm altogether to find the value of phi of m. But if it is a prime number, observation is very clear that phi of m is going to be m minus 1. I hope this is clear. If you are unable to understand what is this phi of m, also what is Euler-Stoughton function, please go through that topic once and then come back here again, right? So whenever m is a prime number, your value of x is going to be a power phi minus 1. Phi is m minus 1, so m minus 2. The value of x is going to be a to the power m minus 2 when m is a prime number. See, if m is a prime number, then GCD of a and m is going to be 1, provided a is less than m, right? Usually this happens in competitive programming. Value of m is usually 10 to the power 9 plus 7, something like that. So the value of a is usually less than m. So GCD of a and m is going to be 1. And m is usually a prime number. So remember, value of x is a to the power phi minus 1, right? Phi minus 1. The value of phi is m minus 1 when m is a prime number. So x is going to be a power m minus 2. Now as I said, usually in competitive programming contest or a usual problem, you will find m as 10 to the power 9 plus 7 or something like that, a big prime number. So computing a power m minus 2 mod m is going to be very hectic, right? You cannot take this time. So definitely we are going to compute it by using binary exponentiation. Please do watch that video. If you don't know what binary exponentiation is, I will add it into the card. So here a is a, here you have m. We compute a power n, where n is m minus 2 in this case, right? So if you just pass to this function m minus 2 in place of n, you will get the value, you will get the result as a modular multiplicative inverse of a. I hope this is clear. So you have two different options. You directly use extended Euclidean algorithm, or you can use this phi, Euler-Stoughton function. What usually you see is, if m is a prime number, then you can directly go and use Euler-Stoughton function, that is a power m minus 2. That's the general case. But if it's not, you can directly use extended Euclidean algorithm, and it's very easy to code as well. Euler-Stoughton function is also very easy to code. That is separate topic altogether. But this makes sense, right? If m is a prime number, go with this approach. You can directly compute a power m by m minus 2 mod m. And if m is not a prime number, then go with extended Euclidean algorithm, because it also checks the GCD as well.